Welcome back to another video. Here, we will talk about normal confidence interval on a single sample. As we know with the point estimators, the true mean is unlikely to be exactly equal to your estimate, and they cannot tell us how far we are from the actual parameter. Here, we will look into how to use probability distributions to define confidence intervals. We want to find a confidence interval on the population mean when the variance is known. So, suppose we have a random sample of size n, x1 to xn, with an unknown population mean, mu, and known variance, sigma squared. Please note that when we claim a sample is IID, the observations are made independently and come from the same identical distribution. For small sample sizes, these observations should be from a normal distribution, while for larger sample sizes, because of the central limit theorem, they can be from any distribution. Given that x bar follows a normal distribution with parameters mu and sigma squared over n, we can standardize it by subtracting the mu and dividing it with sigma over square root of n. This gives us a sample statistics which we can use to define our confidence interval. To have a confidence interval around the population mean, we need to find lower and upper bounds, where the probability of mu being within these bounds are predefined as 1 minus alpha. The lower and upper bounds give us the range of the interval, while the probability gives us the confidence of the interval. To define these lower and upper bounds, we use our statistics of choice that follows a standard normal distribution. To build the confidence interval, we will push half alpha to the right tail of a standard normal distribution, and the corresponding z-value on the z-axis will be z of 1 minus half alpha. The index of z-value is defined as 1 minus half alpha because the probability of a random variable z being less than z-value of 1 minus half alpha is 1 minus alpha over 2. Or alternatively, the area under the curve prior to this z-value, the red area, is 1 minus half alpha, as the total area under the curve for any PDF should equal to 1. Similarly, we push another half alpha to the left tail. With a similar logic, we can say the index of z-value on the z-axis this time would be z of half alpha. Taking advantage of symmetry of normal distributions, we can also claim it is the negative amount of z of 1 minus half alpha. This further simplifies our calculations. Now, we can see that the probability of any random variable z being between negative and positive values of z of 1 minus half alpha equals to 1 minus alpha. If you remember, we started by attempting to define lower and upper bounds, where the probability of mu being within these bounds is 1 minus alpha, and what we currently have is the probability of z being between lower and upper bounds equals to 1 minus alpha. Now, we need to make changes within the parentheses to define the bounds around mu instead of z. To do so, we replace random variable z with our statistics of choice. Now that we have a function of mu in the middle, we can apply some simple mathematical operations to isolate mu. We multiply all sides of these inequalities within the parenthesis with sigma over square root of n, subtract x bar from all sides, and finally multiply everything by a negative 1. Please remember that multiplying an inequality by a negative 1 would result in the inequality signs to flip. Having a closer look, we can see that we achieved our goal. We have successfully defined lower and upper bounds for mu, ensuring that the probability of mu being within these bounds equals to 1 minus alpha. This is the formula for 1 minus alpha, % two-sided confidence interval around the population mean when the variance is known. To build this confidence interval, we need to have these four. First, we need to plug in the population standard deviation. If you remember, we made the assumption that the population variance is known. So luckily, we should know this population parameter. Next, we need to find the sample mean, x bar, and sample size, n. We can find these values as soon as we collect a sample. Finally, we need to identify or set the confidence level. Once the confidence level, 1 minus alpha, is set, we can use Python to find corresponding z-value of 1 minus half alpha. Remember that 1 minus half alpha is the index that helps us to locate the z-value. For example, if the confidence level is 95%, it means that alpha is 5%. So, we need to find z-value of 0.975, which is 1.96. Or, to find a confidence level of 99%, it means that alpha is 1%. So, we need to find z-value of 0.995, which is 2.57. The symmetry of the normal distribution simplifies the process, as it allows us to determine only a single z-value. If the normal distribution were not symmetric, we would need to calculate both z-values, one for half alpha and another one for 1 minus half alpha. Let's go over an example together. Students have participated in a survey regarding their height, and we have access to the sample data. We are asked to find a two-sided 95% confidence interval on the average height of the students, given that the standard deviation is known as 9.48. First, we need to identify the population parameter of interest. As the question is asking us to construct the confidence interval on the average height of the students, we know the population mean is the parameter of interest. Second, we need to confirm whether the population variance is known, and the answer is yes because the question tells us, given that the standard deviation is known as 9.48. So, we know that we need to construct a two-sided normal confidence interval around the population mean, using a single sample when the population variance is known. We can do this either by hand or by using Python functions. If we want to find the interval by hand, we need to have the population variance, find the sample mean and sample size based on the given sample, and use Python or normal tables to find the z-value. By plugging in these values, the confidence interval would be an interval starting at 170.90 and ending at 177.63. Alternatively, we can load the confidence interval norm single function and pass its arguments, such as the dataset, standard deviation, confidence alpha level, and the type, to get the confidence interval. Please remember two important notes. First, although the question has not exclusively mentioned the data is from a normal population, we assumed sample means normality due to having 30 observations and central limit theorem. Second, although we can manually calculate everything by hand here, we cannot do that if the dataset is big. So please learn to work with a programming language, such as Python, to handle larger datasets. In interpretation of confidence intervals, please note that the confidence level highlights the percentage of confidence intervals that would contain the population mean. For example, a 96% confidence interval means out of each 25 confidence intervals created, one will not contain the population parameter. Sometimes we are interested in finding the appropriate sample size for a given significant level and potential error range. In that case, we can define a range of error such as E, which is the potential difference between sample and population means. In that case, sample size and would be square of z-value of 1 minus half alpha multiplied by the population variance divided by the error range squared. Instead of having two-sided confidence intervals, we can also define one-sided ones. This means that there are cases where we want to bound the population parameter of interest only on one side. The only thing different in our approach is that instead pushing half alpha in each tail, we would push the whole alpha in a single tail. That's how we can get two one-sided confidence intervals. One from negative infinity to x bar plus z-value of 1 minus alpha times sigma over square root of n. And another from x bar minus z-value of 1 minus alpha times sigma over square root of n to positive infinity. Thank you for listening to this short lecture on normal confidence intervals on a single sample.